I'm Jeff Groh, and this is Differential Equations, Lecture 2. We're going to begin with the definition. A function of two variables, let's say x and y, is called separable if it can be decomposed in the following way. The function can be expressed as a function of x times a separate function of y. So you can separate the variables into separate factors. Factors, you'll recall, are multiplied together. So you'll have all of the x's here times all of the y's. On the other hand, a differential equation is called separable a differential equation of the form y prime equals some function of x and y is called separable if the function f is separable as a function. Now, why is this any good? It turns out that if your function f is separable and can be expressed as a function of x times a separate function of y, then why is this any good? If I have a differential equation that I can write in this, then I can separate out. Why is this any good? If I have a differential equation that is separable, where I have all the x's here and all the y's over here, then I can rewrite this by putting the y's on the left multiplied by a dy and the x's on the right multiplied by a dx. This allows me to integrate both sides, and then I'll find some function of y on the left equaling some function of x on the right, and that gives me a complete solution to separable differential equations. The only impediment is that you have to know how to integrate each side. So you have to be sharp on your techniques of integration. Which techniques do you need to remember from Calculus 2? You need all of them. In fact, let me break it down for you. This may help a little bit. When you look at an integral, first thing you should check is see if there's anything, the derivative of anything lying around. If there is, you can do some kind of substitution. Second, if the integrand is a rational function, meaning it's the ratio of two polynomials, a polynomial divided by a polynomial, then you can use the method of partial fractions. Third, if you see the sum or difference of squares under a radical, then the indicated method of integration is a trigonometric substitution. Unless you see the derivative of something lying around, in which case you might do a regular old U substitution. And as a last resort, you need to know integration by parts. If none of the other three methods work, it's probably an integration by parts problem. So, let's try some simple examples. Suppose I have the differential equation dy dx equals y divided by x. The right-hand side can clearly be expressed as 1 over x times y, and hence this equation is clearly separable. We can separate the variables by rewriting this as 1 over y dy equals 1 over x dx. Just based on this form alone, since everything on the left is arranged in exactly the same way as everything on the right except for a different variable, you might guess that the solution is something on the order of y equals x. Let's see what happens. we get the natural log of the absolute value of y equals the natural log of the absolute value of x plus an arbitrary constant of integration. We can exponentiate both sides, and then we get the absolute value of y equals a constant times the absolute value of x. This has solution y is plus or minus a constant times x, or y is a constant times x. Another example, suppose you have dy dx equals minus x over y. Now, we separate the variables by writing this as y dy equals minus x dx and integrate both sides. On the left-hand side, we'll have y squared over 2. On the right-hand side, negative x squared over 2 plus a constant. We can rearrange this solution in this way. Multiplying both sides by 2, we can absorb the 2 on the right-hand side into the constant. We get x squared plus y squared equals c, meaning that the solutions happen to be circles. For another example, let's suppose we have dy dx equals 1 plus y squared over 2xy. Again, you can see that this can be expressed as 1 over x times the fraction 1 plus y squared over 2y. If we rewrite this as 2y divided by 1 plus y squared dy equals 1 over x dx, we can easily integrate both sides. On the right-hand side, we get natural log absolute value of x plus c. On the left-hand side, you can see that the integral is of the form f prime over f, and we've already seen in the last lecture that in all cases, that can be expressed as the natural log of the absolute value of f plus c. You can see then that the solution to the differential equation is of the form the log of 1 plus y squared in absolute value equals the natural log of the absolute value of x plus c. We're not going to solve for y explicitly as a function of x. It's clear that you can solve for y as a function of x. Also, note that in this particular instance, since 1 plus y squared is already non-negative, the absolute value on the left-hand side is superfluous. You may use parentheses there instead. In our next example, we're going to have dy dx equals 1 plus y squared over x. This is, again, separable. However, it separates out in the following way. 1 over 1 plus y squared dy equals 1 over x dx. The right-hand side can be solved as before, but the left-hand side is a little bit different. The left-hand integral is a special one that you should remember. In particular, there's an integral that I call the 1. You're going to be married to this integral forever after. If I'm integrating 1 over 1 plus x squared, I get arctangent of x plus c. And so for us, and so on the left, we get arctangent of y. You need to be careful if you want to solve for y here. When you solve for y, you have to take the tangent of both sides. The tangent of the arctangent cancels out, but on the right-hand side, you need to make sure that you take the tangent of the entire right-hand side, not just of the first term. Some students make that mistake. For tangent, you have a whole special identity for sums of angles, and you would have to apply that here. In our next example, we're going to have dy dx equals y over the square root of 1 minus x squared. Note that it is good form to put a downward flange at the end of your square roots. Engineers should always do this. I have a calculator designed for engineers, and on the square root button it has that downward flange. So I'm not just making this up. Students often write their square roots badly, and it's unclear where the square root ends. To be sure that you know, and the people who read your work also know, where that square root ends so that your structures don't fall down, you need to put a downward flange at the end of your square roots. Now, we can separate out the variables. 1 over y dy equals 1 over the square root of 1 minus x squared dx, and then integrate. The integral on the left-hand side this time is pretty easy. It's the integral on the right-hand side that you need to remember. That's the other one that I want you to remember. I want you to know that if you integrate 1 over the square root of 1 minus x squared, you get the inverse sine of x plus c. The solution to the differential equation is the log of the absolute value of y equals the arcsine of x plus c, and we will be content to leave our answers expressed implicitly in this form. In the next example, we'll have the derivative is 1 minus y squared over x. This is similar to a problem that we solved just a moment ago with the 1 plus y squared. And we separate the variables in the same way, but the solution method is different. We get the same thing on the right, to be sure, log absolute value of x plus c. But on the left-hand side, we don't get the same thing. It's not going to be arctangent because of the minus. This is not the 1. Instead, you have to approach this as though we have a polynomial divided by a polynomial. That polynomial in the denominator can be factored, and so the right method of integration is partial fractions. So we're going to express this first as 1 over 1 minus y times 1 plus y, all times dy. Partial fractions is really an algebraic technique meant to separate out complicated fractions, rational expressions, into the sum of simpler rational expressions. In this particular case, it's pretty easy to figure out how to separate these. If I have 1 minus y here, and some fraction with the denominator of 1 plus y here, you might be able to figure this particular partial fractions problem out in your head based on how it is that you add fractions. If I have a fraction a over b, and I'm adding that to c over d, what I have to do is have a common denominator. And so I'd write this as a over b times d over d plus c over d times b over b. And this gives me AD plus BC over BD. In other words, you multiply this denominator, the denominator on the right, to the numerator on the left, and the denominator on the left to the numerator on the right, and then just multiply the denominators. You multiply this way, and this way, yielding this. On our particular fraction, we need to know what these numerators might be. I need them to be such that when I multiply them out, I end up with a numerator of only 1. That means the y's have to cancel out, and that means that whatever these numerators are, they're the same magnitude. They're the same thing. If this is, say, 2, and this is 2, I'll have a 2y when I distribute, and a negative 2y, and the y's will cancel. Unfortunately, if the numerators are both 2, I'll have a 2 times 1, which is 2, plus another 2 times 1, which is 2. I can end up with a numerator of 4, which is wrong. So 2 is not the right thing. But if you think a little bit, you can see that the numerators have to be both 1/2. That way, when I multiply this over to here, I'll get 1/2 times 1. When I multiply this over to here, I'll get 1/2 times 1. 1/2 plus 1/2 is 1. And that is the solution to the partial fraction decomposition. Now, I recognize that some of you won't be able to do this in your heads right off. And so we're going to go through this the old-fashioned way as well, so you can have a review of how the method of partial fractions works out. I wanted to show you how to do a partial fraction decomposition in your head, because some of you won't give yourselves mental permission to do it unless you see someone else doing it as well. Some of you will catch on to that, some of you won't. In the old-fashioned method, we'll assume that the numerators are some constants a and b that we have to figure out. Now, to proceed from here, we multiply both sides by the denominator on the left-hand side. Whole thing, 1 minus y, 1 plus y here. On the left-hand side, everything cancels and we get 1. On the right-hand side, on the first term, the 1 minus y cancels. I get a times 1 plus y. And on the second term, when we distribute, the 1 plus y cancels. I get b times 1 minus y. From here, this equation must be true for all values of y. And in particular, it has to be true for any particular values of y that we choose. Why don't we set y equal to 1? If I set y equal to 1, b is going to cancel. So I'll set y equal to 1, and as a consequence, I'll get 1 equals 2a. If I put 1 in here, 1 plus 1 is 2, I get 2 times a. That implies that a is 1/2. I'll put that in a little bucket here. The next obvious choice for y is y equals -1. So if y is -1, this term will cancel out. The left-hand side will still be 1. On the right-hand side, I'll have 1 minus -1. I'll end up with 2b. That clearly implies that b is 1/2. I'll put that in a little bucket over here too. Collecting our results, we'll have the natural log of the absolute value of x plus c is the integral of 1/2 1 minus y plus the integral of 1/2 over 1 plus y dy. Now the second integral is pretty easy because the derivative of 1 plus y with respect to y is 1. So that integral will be 1/2 log absolute value of 1 plus y. On the first integral, the derivative of 1 minus y is -1. So I need to rewrite that as -1/2 the integral of -1 over 1 minus y dy. Then I can easily find the answer, -1/2 log absolute value of 1 minus y plus 1/2 log absolute value 1 plus y. All of that equal to log absolute value of x plus c, and that is our solution. In the next example, we'll have the derivative dy dx equals xy divided by the square root of the quantity 1 minus x squared. Yes, we can separate the variables easily enough. 1 over y dy equals x over the square root of 1 minus x squared dx. What is the method of integration? Name the method. Remember, we have substitution, partial fractions, trigonometric substitutions, and integration by parts. On the right-hand side, correct method of integration, because you have the derivative of something more or less lying around, is u substitution. You should choose u equals 1 minus x squared. If that's the case, du is minus 2x dx. We don't have the -2, so we can divide that off. And then the integral on the right-hand side is transformed into -1/2 1 over the square root of u times du, or minus 1/2 the integral of u to the minus 1/2 du. From here, we can use the power rule for antiderivatives. Remember, you add 1 to the exponent and divide by the new exponent. The negative 1/2 out front is coming along for the ride. We're going to have u to the positive 1/2. When we divide by 1/2, that's the same thing as multiplying by 2 plus a constant of integration. From here, we substitute back, getting negative square root 1 minus x squared plus c equals log absolute value of y. We'll leave our solution in this form. And as another example, suppose we have dy dx equals y times the square root of 1 minus x squared. Separating the variables, 1 over y dy is the square root of 1 minus x squared dx. Now, that left-hand side, we've seen that often enough, but what is the method on the right-hand side? Let's see. If we run through the list, I don't see the derivative of anything lying around. I don't see a rational function there. Rational functions, what are those? Functions that talk and make sense? No, remember, polynomial divided by polynomial. That's not what we have here. It looks like a difference of squares under a radical, so this is definitely a trigonometric substitution. Because of the form 1 minus x squared, we need to use a Pythagorean identity of the form 1 minus trig function squared equals trig function squared. So the substitution is x equals sine theta. We need to use a different variable, theta. If that's the case, dx will be cosine theta d theta. The integral on the left is trivial enough. On the right, we'll have the square root of 1 minus sine squared theta, but the dx gets replaced by cosine theta d theta. Well, 1 minus sine squared is cosine squared theta by the Pythagorean identity. The square root of cosine squared is cosine. So the right-hand side simplifies to cosine squared theta d theta. Here, you need to remember your half-angle identities. In particular, you need to know that cosine squared theta is 1/2 times the quantity 1 plus cosine 2 theta, and also sine squared theta is 1/2 times the quantity 1 minus cosine 2 theta. For us, we get 1/2 times the integral of 1 plus cosine 2 theta d theta. When we integrate that, we get 1/2 times the quantity theta plus 1/2 the sine of 2 theta plus c. And from here, we need to use the double angle identity for sine. We need to use the fact that sine of 2 theta is 2 sine theta cosine theta. Then we get log absolute value of y equals 1/2 times the quantity theta plus 1/2 times 2 times sine theta cosine theta plus c, where the 2's here cancel out. Now we need to remember that we chose the substitution x equals sine theta. We should write this as x over 1 equals sine theta and draw a little triangle. If this is theta, sine is opposite over hypotenuse. So the opposite will be x and the hypotenuse will be 1. By the Pythagorean theorem, the adjacent side is the square root of 1 minus x squared. We finally deduce that the one-parameter family of solutions to our differential equation is log absolute value of y is 1/2. Solving for theta here, theta is going to be the inverse sine of x, plus sine theta is x, cosine theta is adjacent over hypotenuse. So cosine theta is going to be the square root of 1 minus x squared plus c, and this will be our class of solutions. What are the methods of integration that we have reviewed so far? We've done substitution, we've done a partial fractions decomposition, we've done a trigonometric substitution. What we haven't done is an integration by parts. So I want to give you an example which will illustrate a really nice method for integration by parts called the tabular method. Suppose I have the differential equation, let's say x cubed e to the 2x divided by y. In this case, the variables separate out very nicely. We'll have an x cubed e to the 2x dx. You can see pretty quickly that this is definitely going to be an integration by parts problem. But because we have a cube, we're going to have to apply the method 3 distinct times. However, the tabular method allows us to do all 3 of those at the same time, saving us a lot of work. The left-hand side is just easily enough, y squared over 2. So let's see about this integral, x cubed e to the 2x dx. For an integration by parts problem like this, you need to choose a portion u that you're going to differentiate and a portion dv that you're going to integrate. U in this case is x cubed because that's the part you'd rather differentiate, and dv will be e to the 2x. We'll differentiate down the first column. We'll have 3x squared, 6x, 6, and then finally 0. That's where you stop. When you integrate e to the 2x, remember, first of all, you're integrating, not differentiating. You get 1/2 e to the 2x. You divide by that coefficient of x, 2. When you integrate again, you'll get another half, so you get 1/4 e to the 2x. And on the next line, you get 1/8 e to the 2x and 1/16 e to the 2x. Now that we've completed the table, you need to multiply down diagonals, but alternate in sign, plus, minus, plus, minus. The solution will be x cubed over 2 e to the 2x minus 3/4 x squared e to the 2x plus 6/8 x over, let's see, e to the 2x, and then minus 6/16 e to the 2x plus c. All of that equal to y squared over 2 gives us the solution. What if you're presented with a differential equation that you can't integrate? It might still be possible to get an idea of what the solutions do by a method called direction fields or slope fields. The idea behind this method is that if you have a differential equation of the form dy dx equals some function of x and y, then at each point in the plane xy, you can plug that point in to the right-hand side and determine the slope of any solution curve passing through that point. So at each point in the plane, we might be able to attach little slopes. So we might have little slopes here, and maybe other little slopes here, and slopes over here, slopes on this side, maybe something like this, etc., etc. And if you follow these, you might be able to then determine what path the solution curve might follow. As a quick example, suppose I have the differential equation dy dx equals minus x over y. You might remember that earlier in this lecture we actually solved this differential equation and found that the solutions are circles. Let's try this out. Notice that everywhere that y is equal to 0, everywhere on the x-axis, the slopes are undefined. We might even put vertical line segments at different points here. Whereas when x is 0 on the y-axis, the slopes are 0. At the point 1, 1, if I plug in x equals 1 and y equals 1, the slopes will be negative 1. The same will be true at 2, 2, slope of negative 1, and at 3, 3, also a slope of negative 1. Everywhere on the line y equals x, I will have a slope of negative 1. When x is negative 1 and y is positive 1, negative 1 here, positive 1 here, the slope is positive 1. In fact, everywhere where y is equal to negative x, we get a slope of positive 1, like this. Suppose I'm looking at the point 3, 1. If x is 3 and y is 1, I get negative 3 divided by 1. I get a slope of negative 3, which is pretty steep. If I'm looking at the point 1, 3, x equals 1, y equals 3, I get a slope of negative 1/3. Not very steep. I think you can see that the solution curves are going to go around something like this. The solution curves are circles. For another example, let's look at a curve, a differential equation, in the form of something called the Logistic Equation. We're going to assume m is just some known constant. If this were a population, we would be thinking the rate of change of the population is, well, proportional to the size of the population, not just proportional, but equal to the size of the population times some constant m minus y. Notice that if y is less than m, this difference is positive, in which case our slopes will be positive. If y is greater than m, this difference is negative and the slopes will be negative. But if y equals m, the slopes will be 0. We kind of think of m as the maximum sustainable population size. Also, if y is equal to 0, if you're on the x-axis, the slopes are 0. So there are two places where the slopes end up being 0, y equals m, and y equals 0. Between 0 and m, the slopes are positive, and as you get closer and closer to m, the slopes get closer and closer to 0. We get closer and closer to 0 as we get up here. If you're above m, the slopes go negative. And the further up you get, the more negative. If y is negative, then we'll have a negative times a positive, which gives us negative slopes. That doesn't make sense in terms of populations because we don't get negative population sizes. But remember, this is a mathematical problem, not just some applied problem. Y equals 0, you'll remember, at 0 slope, you might think extinction is pretty stable. Turns out extinction is not that stable. If you bump off of it just a little bit this way, you end up trending towards the maximum sustainable population size. If you start above, you'll trend down to the maximum sustainable population size, and if you start below, you'll trend even more negative. There's also something called the method of isoclines. And that's very similar to the direction field or slope field method. It works in the same class of differential equations. But in this case, you set the right-hand side equal to some constant m, some slope. This determines a curve. A single equation involving two unknowns, in theory, could be solved for one of those unknowns. You'll get some kind of a curve. The curve is called the isocline. In this case, you have one slope, the same slope at each point on that curve. So if the curve looks something like this, and the slopes are all, say, 1 at each point as you move along there, you can draw in those little slopes along that isocline. If you choose a different value of m, you'll get a different curve, in which case you might have other slopes, the same slope on that curve. And on another isocline, all the same slopes there. You end up being able to follow those to, I guess, try to figure out what the shape of the solution curve will look like. As an example, suppose we have dy dx equals x plus y. If we set the right-hand side equal to various constants like 0 equals x plus y, you can see that we'll have the curve y equals negative x, and everywhere along that curve y equals negative x, the slope will be 0. So all the way along this line, this isocline, the slopes are 0. If we choose m equals 1, we get 1 equals x plus y, or y equals negative x plus 1. This is parallel, a line with slope of negative 1, intercept of positive 1. That's going to be this line. But everywhere on this line, the slopes of the solution curve will be positive 1. If we choose m equals 2, we get y equals negative x plus 2. That gives us this line, and everywhere on that line, the slopes will be positive 2. So even steeper than before. I think you can see if m is equal to negative 1, you get y equals negative x minus 1, m equals negative 2. We'll have slopes negative 2 all the way along this line. And you can kind of see solution curves will do something like this. They'll go straight along here, or they'll curve away like this. Now I want to talk about first-order linear problems. Remember, differential equations that are linear have the unknown function y and its derivatives once in separate terms in the numerator to the power 1. For linear problems, that means you can always rewrite them in the following form. There's a special method just for first-order linear problems, and it's based upon reversing the product rule. Remember that for the product rule, if you have the product of two functions, the derivative is the derivative of the first times the second plus the first times the derivative of the second. The way this method works is we multiply both sides by some function mu called an integrating factor. We want to choose this function mu so that the coefficient of y is equal to mu prime of x. If that's true, then the left-hand side very much looks like the outcome of a product rule. Derivative of the first times the second plus the first times the derivative of the second. If we choose mu so that mu prime of x is equal to mu of x times p of x, then the differential equation reduces to the following. The left-hand side is the derivative of mu of x times y, and the right-hand side is mu of x q of x. What's nice about this is that if we multiply both sides by dx, we can integrate. The right-hand side just depends upon our ability to integrate the product of two functions. On the left-hand side, we're integrating a derivative, which exactly cancels out. And so we get mu of xy is whatever the integral is over here. And I'll emphasize that we get a constant of integration. We can solve for the function y by dividing by mu of x. Note that on the right, mu of x here is outside of the integral. It cannot cancel the mu on the inside. And this gives us the solution to all first-order linear problems, provided we can figure out what the integrating factor mu is. You're going to memorize this formula. By memorizing this formula, you won't have to rederive the solution every time, and you'll save a lot of time and effort in the solution process. To determine this function mu, we have to solve this differential equation, and fortunately, that differential equation is separable. We're going to rewrite this differential equation in this form. d mu dx equals mu p of x, and separate the variables as 1 over mu d mu equals p of x dx. From here we simply integrate both sides. It turns out for integrating factors you never need to worry about absolute values or the plus c. There are good reasons if you go through the train of thought of what happens with an integrating factor. But we can write the left-hand side as the natural log of mu, and the right-hand side is just the integral of p of x dx, which we can't reduce any further since we don't know some specific function p of x. However, we can exponentiate to figure out what mu has to be. It turns out that in all cases, the integrating factor mu is e to the integral of p of x dx. You're going to memorize this too. To solve a first-order linear differential equation, step number 1, find the integrating factor. Step number 2, once you know the integrating factor, the solution is 1 over mu times the integral of mu q plus a constant divided by mu. That explains the whole method. Let's solve some first-order linear differential equations. Suppose I start with the differential equation y prime plus 2 over xy equals sine x. In this case, p of x is 2 divided by x. It's the coefficient of y. And q of x is the right-hand side, sine of x. The first step in our process is to solve for the integrating factor mu. Mu is e to the integral of p of x, 2 over x, keeping in mind that when solving for the integrating factor, you never need to worry about absolute values or plus c's. This is going to be e to the 2 times the natural log of x, which can be simplified by raising this 2 into this position, ln of x squared, using one of the properties of logs. And then because the exponential function and the log are inverse functions to each other, the integrating factor is x squared. It follows then that the solution to the differential equation is 1 over mu integral mu q dx plus a constant divided by mu. To complete the solution, all we have to do is integrate x squared sine of x. Name the method. If you guessed integration by parts, then you're right. Clearly, we need to differentiate this x squared. If we do this the old-fashioned way, it's going to take 2 integration by parts. But if we use the tabular method, we can save a little bit of time. So let's use the tabular method. For the tabular method, u is the thing that you want to differentiate, and dv is everything else. So on the left-hand side, we're going to differentiate until we get to 0. On the right-hand side, we integrate. What is the integral of sine of x? Remember, we're integrating and not differentiating down the second column. The integral of sine of x is negative cosine of x. And the integral of negative cosine of x is negative sine of x. When we integrate negative sine of x, we'll get negative negative, that's positive cosine of x. In the next step, we multiply down diagonals and alternate signs. So we'll have y is 1 over x squared times, we'll get a negative x squared cosine of x. We'll have minus a negative, that ends up being positive 2x sine of x, and then positive 2 cosine of x, but don't forget the plus c divided by x squared, giving us the solution to this first-order linear differential equation. Let's try another example. Suppose I have y prime minus tangent of xy equals secant of x. Step 1 is to find the integrating factor, which is e to the integral of minus tangent of x. How do you integrate tangent? Well, you have to break it up into sine of x over cosine of x. What is the derivative of cosine x? Isn't the derivative of cosine exactly negative sine of x? This is in the form f prime over f, which means the integral is the natural log of the cosine of x, keeping in mind that we don't need the absolute values or the plus c when calculating the integrating factor mu. The log and the e cancel out, and the integrating factor is cosine of x. If the integrating factor mu is cosine of x, then the solution y is 1 over cosine of x times the integral of cosine of x times secant of x plus a constant divided by the cosine of x. Since secant is 1 over cosine, these cancel out. If I integrate dx, I'll just have x. 1 over cosine is secant, so I end up with x secant of x plus c times secant of x. And that solves this first-order linear differential equation. To solve the differential equation y prime plus tangent of x times y equals 1, we start by finding the integrating factor mu. We need to integrate the coefficient of y, which is the tangent of x. And to integrate that, we need to break tangent into sine over cosine. Unlike in the last example, the numerator is no longer exactly the derivative of the denominator. The derivative of cosine is minus sine of x. I would like for the integral to be in the form f prime over f, so we can easily write down what the integral is. But to do that, I need to make a minus sign here. I get what I want, but I have to pay for it with a minus sign out front. This gives us e to the minus ln of cosine of x. In the integrating factor, the minus can be moved right here using the property of logs. Then we can cancel the e and the log. We'll have 1 over cosine, but that's secant of x. So the integrating factor is secant of x. The solution is y equals 1 over mu. 1 over the secant is cosine, times the integral of mu, which is secant of x, q, which in this case was 1, plus c divided by mu. What is the integral of secant of x? The integral of secant of x, if you don't know it, can be found using what I call a garbage can calculation. The only way to explain what we're going to do next is there must have been some professor pacing in his office trying to figure out what the integral of secant of x is. And as he happened to pass his trash can, he figured there it was exactly what he needed. What he needed was the following. He needed to multiply by secant of x plus tangent of x, but you can't just do that because that changes the value of the integrand. But if you multiply by something that's equivalent to 1, that is permissible. So what good is that? I'm going to distribute, and when I distribute, I'm going to reverse the order of the sum in the numerator using the commutative law of addition. What we get is something that is exactly in the form f prime over f. The derivative of secant is secant tangent, and the derivative of tangent is secant squared. It's exactly in the form f prime over f. It follows immediately then that the integral of secant of x is natural log absolute value secant of x plus tangent of x plus an arbitrary constant of integration. We deduce then that the solution to the differential equation is y equals cosine of x times the natural log of absolute value of secant of x plus tangent of x plus the arbitrary constant c times the cosine of x. There is a related class of differential equations called Bernoulli Equations. These have the form y prime plus p of xy equals q of x times y to the n. The key to solving Bernoulli equations is to make a change in variable. U equals y to the 1 minus n. Why does this help? Well, it turns out u prime will be 1 minus n y to the minus n times y prime using the chain rule. If we divide the original equation by y to the n, we'll get y to the minus n y prime plus p of x y to the 1 minus n equals q of x. And you can see certain elements of the substitution above. In fact, the differential equation is transformed into the equation 1 over 1 minus n times u prime plus p of x u equals q of x. There's only one thing left to do to put this into the standard form for a first-order linear problem, but it's clear at this point it will be first-order linear. Multiplying both sides by 1 minus n, we get u prime plus the quantity 1 minus n p of x u equals 1 minus n q of x. We get this first-order linear equation based on the substitution u equals y to the 1 minus n. For example, consider the Bernoulli equation. Let's say x squared y squared on the right-hand side. In this particular instance, n is equal to 2, which means u is y to the power of 1 minus 2, or 1 over y. The differential equation is transformed into u prime plus n minus 1 minus n, in this case is negative 1, times p, times 1 over x times u, and that equals 1 minus n times the old q, which is x squared, a first-order linear problem. To calculate the integrating factor, we do e to the integral of negative 1 over x dx, and that gives us e to the minus ln of x. Now I have to caution you here, I've had a lot of students screw up in simplifying e to the minus ln of x. One thing they do wrong is they think they can just cancel the e and the log now, but they can't. You have to move the negative 1 up first to e to the ln of x to the negative 1. Then you can cancel. The answer is mu equals 1 over x. With this integrating factor, we can write down the solution u, which is, by the way, 1 over y, equals 1 over mu, 1 over 1 over x is just x, times mu times this q, which is negative x squared, plus c divided by mu, which is c times x. By making a cancellation and integrating, we get 1 over y is minus, when we integrate x, we get x squared over 2, but we're multiplying by another x, we'll have x cubed over 2 plus c times x. An important aspect of differential equations is the question of existence of solutions and uniqueness. We sometimes abbreviate this with the backwards capital E and an exclamation mark. The backwards capital E is the logical quantifier there exists, and the other logical quantifier is an upside down capital A, which means for all, whereas this symbol kind of like symbol of surprise that something happens, and that's because it's so unique. This is the symbol for uniqueness. When it comes to questions of uniqueness, we know already that differential equations typically have an infinite family of solutions. We're usually referring, in regards to uniqueness, to initial value problems. Is there a single solution curve that passes through a given point in the plane? Let me show you an example of a differential equation that has no solution. Consider the differential equation dy dx equals 2y over x, and let's suppose that y of 0 equals 1. I claim that this initial value problem has no solution. It's pretty easy to check because the equation is separable. In particular, 1 over y dy is 2 over x dx, and we simply integrate that. The integral on the left-hand side is ln absolute value of y, and on the right-hand side we get twice ln absolute value of x plus c. Now, we can solve for y by exponentiating. We'll move the 2 into this location, and we'll get y is a constant times x squared. But we also need to account for the initial data. And that gives us, when x is 0, y must be 1. But there is no solution to this equation at all. So we deduce that no solution exists. A natural question that arises is, how can you guarantee that a solution actually exists to an initial value problem? This is important because these differential equations model physical situations. And if you're trying to model a physical situation using an initial value problem that has no solutions, then your model is worthless. So, under what conditions can we guarantee existence of a solution? But existence is only one factor. We expect there to be only one physical outcome to a particular system or model. If there are multiple solutions to the mathematical model, how do you decide which one is the physical one? Nature should choose one. So, we want more than just existence of a solution. We would like the solution to an initial value problem to also be unique. The answer is provided by a theorem called Picard's theorem. Picard's theorem says that for the initial value problem, y prime equals f of x y, y of x naught equals y naught, meaning that the solution curve passes through the point x naught, y naught, if the function f of xy and its partial derivative with respect to y, if these are continuous, on an open rectangle containing the initial point x naught, y naught, then there will in fact exist a unique solution to the initial value problem. And the domain of definition for this solution is the interval x naught minus h to x naught plus h for some positive number h. Now, the theorem, Picard's theorem, is great because it gives us what we need, existence and uniqueness, but it's really bad because it only gives us existence and uniqueness on some small interval of definition for the solution function, and it doesn't really tell us how big that interval is. It could be some very small h indeed on which that solution arc exists, but at least we know that there will in fact exist one and only one solution arc through that initial point. As an example, consider the initial value problem. Y prime equals xy, y of 0 equals 0. In this particular instance, the function f is x times y. Now, the function x times y is a polynomial of degree 2. If you have more than one variable, you add the exponents to get the degree of a particular term. 1 plus 1 equals 2 in this case. And polynomials are continuous across their domain of definition. The domain of definition for this polynomial is the entire xy plane. So certainly on any rectangle about the point 0, 0, the origin, this will be a continuous function. If you look at the partial derivative of f with respect to y, you hold x constant in taking this derivative, and so x just comes along for the ride. The derivative of f with respect to y, you take the derivative of y with respect to y, which is 1, and multiply by the constant x. This too is a polynomial, and hence the initial point 0, 0, we can put any little open rectangle that we want around that. Our theorem, Picard's theorem, guarantees the existence of a solution curve that will go through that point. Before finding what the solution is, just looking at the initial value problem, can you tell me what the solution is? Notice if I plug the point 0, 0 in on the right-hand side, we get a slope y prime equal to 0. Could it be possible that a solution that is constantly 0 will solve this initial value problem? Certainly it satisfies the initial condition, but does it satisfy the differential equation, a function of y identically equal to 0? Well, such a function would have derivative equal to 0 everywhere. And if y is equal to 0, doesn't matter what x is, the right-hand side is going to be 0 as well. So it's easy to check y identically equal to 0 is a solution to the initial value problem. But by the Picard existence uniqueness theorem, we know that this is the only solution, the one and only solution. Let's go back and solve this, though, in a more straightforward manner. This differential equation is clearly separable, so we can separate the variables and integrate. We can separate the variables as 1 over y dy equals x dx, and then integrate. You can see that we get natural log absolute value of y equals x squared over 2 plus a constant. Exponentiating both sides, we get y is a constant times e to the x squared over 2. Now, we also have to solve the initial condition, y of 0 equals 0. But if x is 0, what solution is there to this equation? E to the 0 is just 1. 1 times c is c. We'd have to have c equal to 0. That means y is 0 times e to the x squared over 2. And that's just the function that's 0 for all x, verifying that the solution to the initial value problem is y identically equal to 0. Let's look at another example. Suppose I have dy dx equals x times the square root of y of 0 equals 0 as my initial value problem. You can also see from this particular example that y identically equal to 0 is a solution to the initial value problem. But let's go about solving this the old-fashioned way as well. On the left-hand side, we may wish to express the integrand as y to the negative 1/2. And then we get 2 y to the positive 1/2 equals x squared over 2 plus c, keeping in mind that the solution has to satisfy the initial condition y at 0 equals 0. When we plug in 0 for y and 0 for x, we get c equals 0. That gives us y to the 1/2 is x squared over 4. To simplify this, or to solve for y, we can square both sides, yielding y equals x to the 4th over 16. But wait a minute. I thought we already had a solution y identically equal to 0. But here's a second solution to the differential equation. How is it that we're not getting only one solution, we're getting two? Let's back up and examine the original differential equation. The original initial value problem was y prime equals x, square root of y of 0 equals 0. The function f of xy in Picard's theorem is x times the square root of y. Now this function has problems. In particular, when y is negative, we don't get real answers. So in the xy plane, if our initial point is at 0, 0, we can only have open rectangles above the axis, but not below, because the function is not defined down here. At least it does not give real values down there. In addition, if you take a look at the partial derivative of f with respect to y, the derivative of the square root of x is 1 over 2 root x. The derivative will be x over 2 root y. Not only are we required to have y greater than or equal to 0, but y can't be equal to 0 either. This function is not continuous when y equals 0. So we have to eliminate this whole line, y equals 0. And our initial point is exactly on that line. Again, the hypotheses of Picard's theorem require that both f and the partial derivative of f with respect to y be continuous on an open rectangle containing the initial point. We see that that is not the case for this particular initial value problem, so Picard's theorem doesn't apply, and it does not guarantee uniqueness of solutions or existence. In this particular case, we found that there is one solution, and then we found a second independent solution. We found two solutions to the initial value problem. So existence is not the issue here, it's uniqueness that fails. Picard's theorem doesn't say anything about this particular initial value problem, though, since the hypotheses don't hold. For linear differential equations, there is another existence uniqueness theorem that is more satisfactory than Picard's theorem. So I'm going to write existence uniqueness in front of this theorem. It goes like this. For initial value problems, if P and Q are continuous on an open interval I, where x naught is inside of that interval, then there will in fact exist a unique solution to the initial value problem. There will exist a unique solution to the IVP. The solution may exist on an interval larger than the interval I, but it will for sure exist on the entire interval I. That's better than Picard's theorem, which told us that the solution existed on some interval, but that interval could be quite small. And it gives us no indication of how to find how small that interval is or how big that interval is. In this case, we know that as long as P and Q are continuous on some open interval I, then the solution will be defined, will exist, be unique, and be defined on the entire interval I.